Good morning to all. Today, let's discuss about dinuclear metal clusters of rhenium, copper, chromium and multiple bonding in Re2Xa2-. So what are metal clusters? They are polymetallic complexes that form direct metal-metal bonds and form triangular or closed structures. So it excludes linear metal-metal complexes and also those cage compounds which do not contain a direct metal-metal bonds. So the first condition to form this metal cluster is the atoms with or metals with large energies of atomization are more likely to form metal-metal complexes, and the metals which contains most refractory metals like zirconium, niobium, technetium, rhenium, etc. forms these kinds of metal-metal clusters. And the second factor is the nature of d orbitals. So the metals with higher oxidation state or higher charge doesn't form a stable metal-metal clusters, because we know that the effective nuclear charge is directly proportional to size of d orbitals. So as the charge of the metal increases, there is a contraction of d orbitals which do not form stable metal-metal bonds. So there should be an effective overlap of d orbitals in formation of metal-metal clusters. Then let's go to dinuclear metal clusters of rhenium to rhenium. The example for the dinuclear metal clusters or cluster of rhenium is Re2Xa2-, and the X suggests X denotes halogen atoms, chlorine, bromine, iodine, etc. And the preparation of Re2Xa2- is by the reduction of perrhenate ion in the presence of H3PO2 and HX. So 2ReO4- in the presence of HX and H3PO2 we get Re2Xa2-. Then coming to the structure of this Re2Xa2- or 2-, the rhenium-rhenium bond distance is 224 pm, and it is extremely short than the rhenium-rhenium bond distance in metallic rhenium compounds or metallic rhenium, which is 275 pm, and the rhenium-rhenium bond distance in Re3Cl9 which is 248 pm. So it is this 224 pm is extremely short in this short. Then comes the eclipsed conformation of Cl. We expect a staggered conformation because we know the staggered conformation is more stable. So but here in this case we get an eclipsed conformation of Cl in the structure of Re2Cl2-. Then coming to the bonding in the case of Re2X2-, Coulthard explained the bonding in this dinuclear complex using delta bonding concept when it comes to the case of Re2X8 or Re2Cl2-. So first one is that the Z-axis. Z-axis of Re2Cl2- is taken as the axis or the bond as a line joining two metal-metal bond or two Re-Re bond. So this line joining Re-Re is taken as the Z-axis, and this Re forms Re forms, or each Re is bonded to 4 chlorine atoms. So Re-Re4, the Z-axis is a line joining the two metals, and each rhenium is bonded to 4 chlorine atoms that are almost in square planar arrangement. So ReCl4, ReCl4, and here it is a delta bonding is forming between Re and Re. Then comes the when we discuss about the ReCl bond, ReCl bond is formed by dsp2 hybrid orbitals. dsp2 hybrid orbitals, they are the d orbital taken here is d x² minus y², s, px and p1. Using this dx square minus y square, s, px and py hybridized to form dsp2 hybrid orbitals, and this using this dsp2 hybrid orbitals, the Re is forming a bond with the Cl minus. Then comes the sigma bond. That is Re-Re bond formation. Let's explain how Re-Re bond formation is taking place here. Re-Re bond formation. So we already said that Z-axis is a line joining the two metal atoms, right? So here Re-Re bond is formed using dz square and p is an orbital that forms d-p hybrid orbitals. So metals dz square and p z orbitals lie along the bond axis and may be hybridized to form one orbital directed towards, that is one orbital is directed towards each other and they get overlap. One orbital is directed toward each other and they get overlap, and the other one is directed in the opposite direction and they are non-bonding in this case. So sigma bonding is forming in between rhenium and rhenium, and this rhenium bond, we know that it is along the z-axis. So dz square and p z orbitals hybridized to form dp orbital, and one orbital is lying towards rhenium and rhenium, and the other one is directed to the opposite side. So this comes as the non-bonding orbital in this case, and it is the bonding orbital, sigma bonding. Then comes the pi bond. The pi bond is formed using dxz and dyz. So pi bond is formed using unhybridized orbitals, and this unhybridized orbitals here is dxz and dyz orbital. So these dxz and dyz orbitals can overlap to form two pi bonds, one in xz plane and one in yz plane. Yes. Then comes the fourth orbital. Fourth orbital is of the fourth orbital. Here we have already used dx square minus y square, dz square, dxz and dyz, and the remaining orbital here is dxy orbitals. So each rhenium atom has one dxy orbital on their side. So they form a sideways overlap. Sideways overlap of remaining d orbitals that result in the delta bond. Fourth orbital is the delta bond. So the sideways overlap of dxy orbitals forms the delta bond. Here we have discussed about the dinuclear metal cluster of rhenium in the case of Re2Xz2-. So other dinuclear metal clusters formed by rhenium are they form a series of carboxyl complexes of the formula Re2RCO2 4 times X2, Re2RCO2 twice X4, which resemble Re2Xz2- in the case of eclipse conformation of chlorine atoms, then extremely short metal-metal distances and quadruple metal-metal bonds. The only difference is that the addition of ligands to overlap with the metal dp hybridized or dp hybrid orbitals which were non-bonding in Re2Xz2-. So here the dp hybrid orbitals are non-bonding in the case of Re2Xz2-, but when it comes in the case of the carboxyl complexes, those non-bonding orbitals now overlap with the ligands and form bonding orbitals. Now let's discuss about the dinuclear metal clusters of copper and chromium. Copper and chromium in the first transition series also form acetate complexes which is similar in structure to the rhenium carboxylate complexes. Like their rhenium analog, they are diamagnetic, that is spin pair. The structure is given by this diagram of 4 copper and chromium dinuclear metal clusters. The specialty of this copper-copper bond is when coming to the copper dinuclear metal clusters of copper, Copper-copper bond distance is 264 pm, which is longer than the metal-metal bond or copper-copper bond in metallic copper, which is 256 pm. Then it is a weak single bond forming in between copper and copper. In the case of rhenium, it was quadruple bonding forming in between rhenium and rhenium. But in the case of copper, it is a dinuclear metal cluster of copper. It is a weak single bond forming in between copper and copper. Then coming to the chromium, dinuclear metal clusters of chromium, it is 236.2 picometer, which is shorter than the metallic chromium, 249.8 picometer. And it is, but chromium bond strength is given by 45 kilojoule per mole, which suggests that it is a strong bond when compared to copper, the bond in copper in the dinuclear metal clusters of copper. So all of this evidence and orbital symmetry suggests that a weak quadruple bonding is forming in between chromium and chromium. In the case of copper, it was a single bond, weak single bond, but in the case of chromium, it is a weak quadruple bond forming. Thank you.